throughout this course, both this semester and next semester, we're going to break down chapters using various functional groups. This won't be the only approach. Sometimes we'll look at classes of reactions as well, but one good way to approach organic chemistry is to look at the chemistry of individual functional groups. So we need to start here with the simplest of organic compounds, and that's alkanes. All right. Alkanes are a class of hydrocarbons that really have no functional groups at all. They're just carbons and hydrogens connected by single bonds. All right. Now, I've used that word hydrocarbon multiple times. As the name suggests, it's something that contains hydrogen and carbon, and pretty much only that. All right. So they're very, very simple compounds. Typically, you have only carbon and hydrogen, and of course, you can add a functional group here by adding like double and triple bonds, or aromatic systems by having, alternating pi bonds. That's something we'll get into in a much later chapter. But my point here is we're going to focus in this chapter on the simplest of these, and that's alkanes. All right. So we call alkanes saturated hydrocarbons because they've got the maximum number of hydrogens, right? Actually, if I go back and you can see some of these unsaturated hydrocarbons, they're called unsaturated because we could add hydrogens across that double bond. We could break that pi bond and use it to form two more carbon-hydrogen sigma bonds, right? But you can't do that with an alkane. There's no pi bonds to break. There's only single bonds, only sigma bonds, and that's it. Okay. Now, when it comes to naming these, all of our alkanes will have the suffix ane, which kind of makes sense. It's derived from that suffix in the name alkane. You'll notice this trend with a lot of functional groups. Basically, they tend to have part of the group name in the root name for the compound itself. For example, alcohols end with all, and so on. The prefixes will tell you the number of carbons. So, for example, the pent in pentane tells you that there are 5 carbons. Okay, so 1, 2, 3, 4, 5 carbons in pentane. Okay, and we'll get into that in a second. All right. So, when it comes to organic compounds in general, we're going to look at common names versus systematic or IUPAC names. I'm going to teach you the IUPAC naming systems for all of these compounds that we cover throughout the year. Just realize that there are also common names for a lot of these things. All right. Now, with alkanes, I think typically you don't see too many common names. The IUPAC names are pretty straightforward, but you'll kind of see that with a bunch of other things later on. Okay. All right. So the IUPAC system, IUPAC here stands for the International Union of Pure and Applied Chemistry. This is the body that basically laid down the rules for naming compounds, just to avoid confusion when different chemists were talking to each other. So that everyone knows what compound you're talking about when you give it a particular name. Okay, so in the IUPAC system, you want to look for the parent chain. The parent chain is the longest consecutive chain of carbons. Now, keep in mind, your molecule might not be drawn in a particular way that makes this easy to see. You have to get comfortable with sort of tracing different paths in your molecule and figuring out which is the longest chain. And don't panic. This becomes way easier with practice. You're going to get more and more efficient at this as you do more practice problems. Okay, but I think when you first start out, you may want to try and do this through trial and error. Okay, so for example, when you're looking at this molecule, I think typically people tend to read from left to right, and they look for the longest continuous zigzagging chain that's in a continuous line. So I think your eyes naturally tend to go, look at this chain over here, 1, 2, 3, 4, 5, 6. right? Obviously, there are longer chains. You may have looked at 1, 2, 3, 4, 5, 6, 7, but you've got to trace out all the different possibilities, and that's when you realize that this chain over here has 9, and that's the longest possible chain. So that's going to be our root or our parent chain when it comes to naming this compound. All right. Everything else that's branching off of it are what we call substituents. So those will factor into the name, but when it comes to the root word for the name, we're going to take the fact that the longest chain here has 9 carbons. All right. So the prefix for 9 is non. Okay. So the name of this parent chain would be nonane. Okay. So that's going to be the root word for this. Now, you do have to memorize these prefixes, and don't panic that it's not going to be wasted effort. It's not like you're going to use this only for alkanes. These prefixes come in handy for all IUPAC nomenclature when it comes to organic compounds. Also, you'll find that while the prefixes for 1, 2, 3, and 4 are a little bit unusual, the prefixes from 5 onwards are your typical Greek geometric prefixes, which hopefully might ring a bell from Gen Chem when you were naming regular covalent compounds. All right, and so you can remember those using. There are a lot of common words that will help bring them to mind. So for example, in the case of pent being the prefix for 5, you can think of a pentagon having 5 sides, or like hex for 6, hexagon, hept for 7. Okay, please note it's hept, not sept. We're using Greek prefixes. Sept is the Latin prefix for 7. Okay, that's why September was the 7th month in the Roman calendar, before they added July and August for Julius Caesar and Augustus Caesar. Yeah, actually, you could probably notice that with the other months as well, like October, November, and December. They're the 8th, 9th, and 10th months, respectively, before they got shifted to forward. So, anywho, I think that's a neat random fact, so you've learned something new today. Anyway, moving on. My point here is that you can use a lot of common names, like, octopus, for example, for remembering oct, or decade for remembering dec, But for numbers 1 through 4, those are probably new to you, and you do have to memorize those. All right, the prefix for 1 is meth. So a 1-carbon alkane is methane. The prefix for 2 is eth. So ethane has 2 carbons. Prop is for 3 carbons, so propane, the same stuff you burn on a gas grill or barbecue grill. That same propane is basically an alkane with 3 carbons. And finally, you have butane. But is the prefix for 4. Okay, so so like in a cigarette lighter, for example, that's the hydrocarbon that you'll find fueling those things. Okay, and you can build up on these. For example, like you can go into the teens by adding, a prefix to dec to indicate what number after 10 you're dealing with. So undec, dodec, tridec, tetradec, and so on. Of course, now notice that here we're getting into the regular Greek prefixes. We don't have the weird ones we have through 1 through 4. To be honest with you, you probably don't have to name things in the teens. So I think as long as you're able to number at least till 10, you should be fine. All right. So we have our root word, right? So for example, here our parent chain has 7 carbons. Okay, so think back to what that would be. Our root word here would be heptane, because hept is the prefix for 7. Now, in the case here, you have more than one option for where you draw your longest carbon chain. You can see here that we have, we could draw 7 carbons connected this way and 7 carbons connected this way. Now, if we can't get anything more than 7, otherwise this would be a moot point, right? If we could get something higher than 7, then that would be our parent chain. And obviously you don't want to get anything lower than 7. You want to go with the longest continuous chain. So 7 carbons is our parent chain. Now, when we have a situation like this where there's 2 options for connecting those 7 carbons, for finding out that longest parent chain, you want to go with the one that produces more substituents, more branches. The reason for this is that if you have more substituents, that means that those substituents in turn will be less complicated and therefore easier to name. All right. So for example, here we have 3 substituents. Okay, one of them has 2 carbons, another has 2 carbons, and this third one has 1 carbon. In this one, which is incorrectly chosen, we have a substituent with 2 carbons, but notice that this substituent here is itself branched. Now, there are times when you do have no choice and you've got to name these things, but if you can avoid it like we do over here, you want to try and avoid it. Okay, now occasionally you can have a parent chain that loops in on itself. It forms a ring, or we call this a cyclic compound. All right, it forms a cycle. Right, so we add the prefix cyclo, but we still keep the same naming convention. We take the number of carbons that are in our ring and add ane to that suffix, to that prefix. Sorry. So in this case, if we have a ring of 3 carbons is propane. But since these 3 carbons are connected in a ring, it's cyclopropane. Okay, and likewise you can have cyclobutane, cyclopentane, cyclohexane, etc. All right, so take a second and try these out. Go ahead and find the longest carbon chain, the longest parent chain in both of these molecules. Okay, so feel free to pause here if you need some more think time. Okay, with the first one, there's more than one pathway, so you probably want to trial and error your way through it. Again, like people have a natural tendency to just read from left to right, and if you're doing that, you're probably looking at at this guy and saying, okay, I've got 1, 2, 3, 4, 5, 6, 7 carbons there. That's a pretty long chain, but can we go longer than 7? So if we go 1, 2, 3, 4, 5, 6, 7. Well, that's still 7. What if we start over here? 1, 2, 3, 4, 5, 6, 7, 8. All right, so there's an 8 carbon chain. Now, we've got 2 options for getting to 8 carbons. We could go 1, 2, 3, 4, 5, 6, 7, 8. It turns out that whichever way you go, whichever of those 2 pathways you choose, you're going to wind up with the same name. Okay, so it actually doesn't matter which way you choose your 8 carbons. But regardless, your root word here is going to be octane. Right? Remember, oct is the prefix for is your prefix for 8. Okay, and so we have that, and then we add that ane ending over there. Okay, now over here we've got an interesting conundrum. We have a ring. And we have relatively long chains here. Okay. Now, the problem with this is you've got to pick one or the other. You cannot include as your longest parent chain something that encompasses both a straight chain like this and a ring. You can't say, oh, I'm going to pick my longest chain, my longest carbon. My longest continuous string of carbons as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that's actually not how it works. You've got to pick one or the other. So what determines this is which is bigger. So let's look at our ring. It's got 1, 2, 3, 4, 5, 6, 7 carbons, right? So this would be a cycloheptane. Okay. Now, since none of these branches have more than 7 carbons, we're going to use cycloheptane as our root word. So again, we use that hept prefix because there's 7 carbons in this ring, and so it's a heptane. And of course, we have to add that cyclo prefix to make it cycloheptane. All right. Once you've identified your parent chain, you now have to name the substituents. Okay, so I mentioned that you could have branches coming off of your longest, your parent chain, your longest carbon chain, and you have to name those. Okay, now there are different types of substituents. We've already seen some that are just branches of carbons. Okay, so carbons and hydrogens. We can have other substituents. You could have, for example, halogens. You could have functional groups. There's lots of different substituents, but for now we'll keep it simple and look just at hydrocarbons. How do we name these substituents? Well, the naming convention is going to be very similar to what we have for naming those parent chains. We're still using the same prefixes based on the number of carbons. The only difference is now we're going to add a suffix il, YL, instead of that ane ending. All right? So for example, over here, we have a 1-carbon substituent. Now, the prefix for 1 carbon is meth, so this is a methyl group. This has 2 carbons, so the prefix for 2 carbons is eth. This is an ethyl group. 3 carbons here, this is a propyl group. Okay, so you've got to use that YL suffix. Okay. So once you have your substituent, you write it at the front or before your parent chain name. So you add it as a prefix in that name. Okay, so here our carbon chain, continuous carbon chain, is this cyclohexane. So we use that as our root word. And here we have 1, 2, 3 carbons, so that's a propyl group. So this becomes propyl cyclohexane. Okay, now please note that, again, it's the longest carbon chain that winds up being your root word. So in some cases, a ring could also be a substituent if it's smaller than one of the branches coming off of it. So here, our straight chain part has 4 carbons, but our ring has only 3 carbons. So the straight chain part is butane, and that's our parent chain. And the ring, which has only 3 carbons, is cyclopropane, but it becomes a cyclopropyl group. Okay, you still have to keep that cyclo prefix to show that the 3 carbons of your propyl group are connected in a ring. Okay, now why is there a number 1 over here? Okay, that's what we call a locant, and we're going to get into that in a second. All right, it'll also beg the question of why don't we have it over here? Again, I'll explain that in a second. Okay, so that being said, looking at our previous example, see if you can name the substituents branching off our main chain. So again, remember, in the case of this molecule on the left, we have our 8-carbon chain. This is an octane parent chain. Okay, there's 8 carbons in a row. And again, there's more than one way to select those 8 carbons. You'll find that whichever way you select it, you'll still have the same substituents branching off. So go ahead and name those substituents. Likewise, here for the second one, you have a cycloheptane as your ring. Name these 3 substituents that are branching off that ring. Okay, so feel free to pause the video here if you need some more think time. Okay, this looks like the answers here have the locants as well, and again, we'll get to that in a second. But basically, if you're having trouble seeing where these numbers are, or where the groups are coming from, I'm going to just circle the parent chain here, and we're going to see what's branching off. Okay, so here's our 8-carbon chain. Okay, 1, 2, 3, 4, 5, 6, 7, 8. All right, so notice that we have a 1-carbon branch here, another 1-carbon branch here. Okay, so those are 2 methyl groups. So that's why it's listed as a dimethyl group. You can use Greek prefixes if you have more than one of the same type of substituent. Okay, over here we have a 2-carbon group. 1, 2, and that's the ethyl group that we see over here. Okay, the numbers, by the way, just say where on your parent chain they're located. Okay, I'll practice, where that comes from. But the point is that if we were to number these carbons, basically, you would see where these numbers come from. So if I were to number this 1, 2, 3, that's why this carbon, this ethyl group over here, is on the number 3 carbon. Okay, and this methyl group is the one that's listed as number 3 here. If we continue on 4, 5, 6, this methyl group is on the number 6 carbon. Okay, that's where those numbers come from. Okay. over here on our cycloheptane, we have an ethyl group. We have another ethyl group, so that's why it's listed as diethyl. Okay, and then this group over here has 1, 2, 3, 4 carbons. Okay, so that's a butyl group. That's where that came from. Okay. Alrighty. I mentioned that sometimes you have complex substituents. Your substituents themselves have substituents. They're branched, okay? And you generally want to select your longest carbon chain to avoid this, but sometimes you can't help it, all right? If we wanted to pick our longest carbon chain and say like, oh, I don't want, a weird branching thing like this, I'll use part of this as my longest carbon chain. And I'd say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, but remember, you have to pick your longest carbon chain. You can't just do it just for convenience. And the problem here is that if you start with this branch here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, you have to select this as your parent chain, even if the resulting substituent winds up being more complex. You just can't avoid that. Picking the longest carbon chain as your parent chain has priority over trying to get less complicated groups. Okay, so that being said, we have to name these, right? How do we name these complex branches? Well, you kind of treat it like, you treat it as having a substituent on the substituent. Okay, let me show you what I mean here. But keep in mind, you don't want to use the same nomenclature that you used for a simpler branch. So if you look at this and say, oh, it's got 5 carbons in it, why can't I just call this a pentyl group? Well, a pentyl group has 5 carbons connected continuously. All right, so if this carbon over here were branching off here, so you had 5 carbons connected in a straight chain, then yeah, that's a pentyl group. But this can't be a pentyl group, okay? Because that would be confusing. If you call that a pentyl group, anyone hearing that name would think that all 5 carbons were connected continuously. So how do we name a substituent within a substituent? So you kind of treat it like it's its own little alkane. So starting from the end that's connected to the parent chain, you start numbering it, which is what we're going to do later on when we have locants, okay, for the parent chain. And you basically then treat, whatever branch you have coming off as another substituent. Okay, so in this case, we have 4 carbons, right? So that's a butyl group. But now we have another carbon, a 1-carbon group or a methyl group, coming off that butyl group. So it becomes a methyl butyl group. Okay, now you've got to say where that methyl group is, and it's on the number 2 carbon. So it is a 2-methyl butyl group. Okay. Now, you want to put that name in parentheses just because otherwise I think if you don't have it in parentheses, if there are any other substituents on your parent chain, it can get kind of confusing when you see all of these things together. Okay? Now, that being said, there are also common names for a lot of these branched substituents. Okay, just to save you hassle. And you've probably heard of a few of these. So I think you probably have heard of rubbing alcohol. Its common name is isopropyl alcohol or isopropanol. Well, the isopropyl group refers to a 1-methyl ethyl group. Okay, so that's, you have a basically it's got 3 carbons, right? But you're connected to the middle carbon instead of the end carbon. So instead of being a regular propyl group, it's called isopropyl. But the IUPAC name would look at this and say, all right, you've got an ethyl group here, right? You've got 2 carbons, so if this is my parent chain, I've got this 2-carbon group that's connected to the parent chain, and now here I have a 1-carbon methyl group branching off the number 1 carbon of my ethyl group. So it's 1-methyl ethyl. Okay. And there are other ones out there. The group we saw earlier, could be, oh, actually, I guess that's a methylpropyl. Oh, there we go. I think I have it on. Um, oh no, sorry, this one's slightly different. If this group were over here, then it would be similar to the example we had earlier. But anyway, my point is that there are groups like sec-butyl or isobutyl or tert-butyl. These are all common names, but especially tert-butyl, you might see that pretty commonly as a substituent. Okay, so even though there are IUPAC names for this, it doesn't hurt to get comfortable with some of those common names, just because you'll run into them quite a bit. Okay. Yeah, here we have isopentyl or isoamyl groups, a neopentyl group. Some of these are less common. I wouldn't stress too much about this. I would say isopropyl and tert-butyl are probably the most common names you would see for these weird branch substituents. Okay, so don't stress too much about some of the more complex ones, but just realize if you do ever come across some of these weird prefix names, these weird substituent names, it might be a complex branch substituent, and you may want to look up these names accordingly. All right, so let's talk about locants. I've kind of already mentioned this a few times, but basically a locant is just a number that's assigned to each of the carbons on your parent chain that allow you to see where your substituents are attached. Okay, so for example, if we have our parent chain as pentane, right? There's 5 carbons in pentane. We number those carbons going, from one end to the other as 1, 2, 3, 4, 5. And if we have any substituents branching off, we can say where they're located. Okay, this is kind of important, especially for distinguishing isomers, for distinguishing two molecules that have the same molecular formula but a different structure. Okay, so for example, here are 2 isomers of methylpentane. They both have that 5-carbon chain for pentane, and both of them have a methyl group branching off. But the molecule over here on the left has its methyl group on the number 2 carbon, so we call it 2-methylpentane. And the molecule over here has the methyl group branching off the number 3 carbon, so it's 3-methylpentane. Okay, and they're very different molecules. Notice this one's way more symmetrical than this one because of where that methyl group's located. Okay, quick point here. Please note that anytime you see a number in a name, that does not mean that's the number of groups, right? It's the location of the group. That 2 there refers to where that methyl group is located. The 3 over here refers to where the methyl group is located. If you had more than one methyl group, use a Greek prefix to state that. So if you had 2 methyl groups, it would be dimethyl. If you had 3 methyl groups, it would be trimethyl. But you would have locants for each of them. Okay, we'll see some examples in a second. Quick note here about numbering. Okay, I think again, people's natural instinct is to number from left to right, just because that's how we read things. You need to. This might not necessarily be the way you number a molecule. So again, just like with the trial and error that comes with figuring out your parent chain, it might also be a good habit to try numbering your parent chain from either end and seeing which name is better. Okay, which one gives you the best possible answer. So why do you have to do this? Well, the key thing is that when you number your when you put your locants for your substituents, you want to have the lowest set of numbers typically. Okay, that's not the best way to describe. That's not completely accurate. I'll go into the more nuanced way of approaching this in a second. But general rule of thumb, typically you try to get lower numbers. Okay, so basically so if you have only one substituent, you want to start numbering from the side closer to that substituent. So it makes having this be 2-methylheptane makes more sense than having it called 6-methylheptane, right? You want to have that, you start numbering from the end closer to the substituent. Okay, now again, this isn't like the proper wording of the rule. This you can see this when there are more than one substituents attached. So for example, here, when it comes to numbering, when you've got more than one set of substituents, you want to start numbering from the side that is closer to any substituent. So basically, if I start numbering from the left, I hit a substituent on that second carbon. If I start numbering from the right, I've got to go 3 carbons before I hit a substituent. So that's why we start numbering from the left. Okay? Even though I wind up having a larger set of numbers, I've got 2 5s and here I've got 2 3s. So that's 12. Actually, I guess in this case, both the sets of numbers add up to 12. So that's probably not a great example. There's some, you may sometimes hear that rule, or people describing this rule as like, oh, I just want the lowest set of numbers. Technically, that's not it. It is possible to do that and get the wrong answer. Okay, so the proper way to explain this is that you want to start numbering this from the side that closer to a substituent. Okay. Okay. So if you're having trouble seeing this, try drawing out like 277 trimethylnonane and then numbering it from the other end. Okay. It'll give you a lower set of numbers, but it'll be the wrong numbers because that first methyl group will not be at number 2. Okay, it would be at like the number 3 carbon if you numbered it from the wrong end. Okay, yeah. So you can see here, basically here we've got a tiebreaker. Okay, in this example. So if you have a tie, then you want to go. You want to go to the next locant. It's just again, it's that same concept. If you want to start numbering from the side closer to where you hit a substituent. It's just that if both approaches tie, then you go to the next available substituent, the next available branch. Okay, so in this case, whether I number from the right or the left, I have a methyl group at that number 2 position. So if I'm numbering from the right, I have a methyl group at the number 2 position. If I number from the left, I've got a methyl at the number 2 position. Okay, but then the tiebreaker then comes with that next substituent. If I'm numbering from the right, that methyl group winds up at the number 3 position. If I number from the left, that methyl group's at the number 5 position. And so this is a better number system. So this would be 2,3,6 trimethylheptane would be the IUPAC name for this. Okay, but that's basically how you want to do this. You want to start numbering. So general rule of thumb is start numbering from the side that has you reach a substituent first. Okay? And if there's a tiebreaker, then you go to the next available substituent that's not tied. Okay. All right. Now, let's say you're still tied. You have 2 substituents at completely symmetrical locations. If there's no other tiebreaker, it ultimately comes down to alphabetical order. Okay, I know that sounds kind of dumb and sounds kind of arbitrary, but IUPAC had to draw the line somewhere, and they said, okay, let's just name things alphabetically. Okay, and assign that the lower number. So the proper way, so here we have a bromine group and a chlorine group, or a bromo or a chloro. Typically for halogens, you take that root word and add an O to the end. Okay, so we have a bromo group and a chloro group, and they're both terminal. They're at the ends of this pentane molecule. So which side do we start numbering from? From the right or the left? Well, we start numbering from the side closer to the bromine because that gives the bromine a lower number. So 1 bromo 5 chloropentane is better than 1 chloro 5 bromo. Okay, because you're going to see in a second that when we name these, we place we write out the substituents in alphabetical order. So I actually said that incorrectly. If we were to name this, it would actually be 5 bromo 1 chloro pentane, because bromo comes first alphabetically, and it looks kind of weird giving that the higher substituent number when there is a way to do it with a lower substituent number without breaking any of our previous rules. All right. Cycloalkanes also follow kind of the same rules, basically. You kind of look at your tiebreakers, right? So again, if we're doing this trial and error if I number it from the left, and this was 1, 2, 3, I have two methyl groups here at the number 1 position and one at the number 3 position. If I numbered it from the right, I have one at the number 1 position and two of them at the number 3 position. And you can see here where that tiebreaker kicks in. Okay, the 1 over here beats out the 3 over here. So it makes more sense to have this be our number 1 carbon. Okay? Alrighty. So basically when you list out your substituents, please try and list them out in alphabetical order. Don't include any prefixes to substituents as numbering them. So, for example, if you have two methyl groups, you'd write dimethyl, but you'd alphabetize that under M for methyl, not D for di. Okay? The only time that I think where a prefix is used to alphabetize something is with iso. So an isopropyl group would be alphabetized with an I instead of a P for propyl. Okay, so let's try naming this example here. So our root name, our parent name, has 6 carbons and it's connected in a ring. So that's cyclohexane, right? The hex is for the 6 carbons. We have 3 methyl groups, right? 1, 2, 3. So that's trimethyl. Becomes trimethyl cyclohexane, and we have a 1, 1, 3 location. So because 2 of them are at that 1 position, and the third one is at the 3 position. I also wanted to briefly draw your attention to how we write out the name. So we write this out as 1,1,3 trimethyl cyclohexane, but note the punctuation here. We use commas to separate out numbers, and we use hyphens or dashes to separate out numbers from letters. And notice that there aren't any spaces or anything between any of our affixes, between any of our prefix and suffixes and so on. It's all one continuous word. Okay, so it's 1,1,3 trimethyl cyclohexane, and we have commas between the numbers, we have a hyphen between the numbers and the letters, but there are no spaces anywhere in there. Okay, so so that basically summarizes how you should approach naming alkanes. Identify their longest carbon chain, use that as your root word, ending, having a prefix reflecting the number of carbons and ending with the word ane, and possibly having a prefix for cyclo if it's a cyclic compound. Identify name substituents. Oftentimes the carbon-based ones have that -il ending. And when you number your parent chain, assign those locants to the substituents. Okay, and then list them in alphabetical order. So with that in mind, go ahead and try these out. Let's have a look at this this molecule up here. Try naming it. Okay, and of course you can pause this to give yourself some more think time. And then after that, we're going to try doing this backwards. We have a name of a molecule here. And we're going to work backwards and try to draw it out. Okay, so go ahead and pause this here if you want to try both these problems. Okay, so in that first example, again, you may need some trial and error to find that longest carbon chain. So you kind of work through all the different pathways through this molecule, and you probably realize that the longest one has 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. Okay, you could get 9 carbons going up here as well, and it doesn't matter which way you go, you'll find out you get the same name. Okay, likewise, instead of starting here, you could have started from here and gone around this way, and you'd still get 9 carbons. So your root word here is going to be nonane. Okay, I find that it sometimes helps to write these names backwards to go start with your root word, put in your prefixes, but like kind of leave space at the beginning of the name to write stuff, to write your prefixes later. Okay? So now that we've got our longest carbon chain here, okay, so here's our longest carbon chain, our parent chain. What are our substituents? Well, we have an ethyl group over here, we have a methyl group over here, we have another methyl group here, and we have an isopropyl group here. Okay, we couldn't make this simpler by selecting a chain going around this way, because then that would one, you would have a more complex system over here, and two, that wouldn't be a 9-carbon chain. So something to watch out for there. Okay, so we're going to name these accordingly. Between ethyl, methyl, and isopropyl, ethyl will come first. Okay, so again, we're going to leave a little bit of a gap to write its locant here. Okay, now between methyl and isopropyl, isopropyl comes next. So again, leave a gap here. I guess we could write isopropyl, or we could use the IUPAC prefix of, since this is an ethyl group, but there's a methyl group coming off of it, this would be 1-methyl ethyl, which you would alphabetize under M, I believe. So next we would have, but we can write this as isopropyl, I think. And then we're going to have 2 methyl groups. So that's going to be dimethyl. I've kind of ran out of room here, so I'm just going to just try and reset that. That's again, let me write out a little bit further down, maybe right down here. So nonane. Okay, I start off with an ethyl group. Leave a little space. I've got my isopropyl group. And then we've got 2 methyl groups, so I'm going to write dimethyl. Okay, and now we want to assign locants. So again, if this is my parent chain, okay, and I'm numbering this, I could start numbering from this side or from this side. I want to start numbering from the right, because that's I go 1 carbon and I hit that methyl group. Whereas here I've got to go 2, 3 carbons before I hit that ethyl group. So we're going to start numbering from the right here. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, and let's see where our things are located. So our ethyl group is this group over here. That's the number 7 carbon, so that would become 7-ethyl. Again, note that we put a hyphen here between the 7 and the ethyl to make this, to not have a space there. Next, we have our isopropyl group. That's attached to carbon number 5. So we have 5 isopropyl, and again, we have hyphens between the number and the letters. And now we have dimethyl. Okay, there are 2 methyl groups. There's one on the number 2 carbon and one on the number 6 carbon. So this would be 2, 6. And again, notice we have hyphens on either side of that. So 7-ethyl, 5 isopropyl, 2,6-dimethyl nonane. Okay, and I pointed out earlier that you could swap out isopropyl here for, 1-methyl ethyl. Okay, in which case this 5-1-methyl ethyl would probably come after the dimethyl, just alphabetically, because methyl ethyl is comes after methyl blank. So you'd probably rearrange this accordingly. With the trying to draw this backwards, what I recommend is, again, to do this problem backwards where you're given a name and you're trying to draw the structure, I want you to try and look at this kind of backwards as well. You want to start with that root word, okay, and draw that parent chain. Now, in this case, your parent chain is cyclohexane. So you have 6 carbons connected in a ring, so just draw a hexagon. Okay. Now, at this point, what you decide as your number 1 position is kind of arbitrary. It's whatever you want it to be. If you're doing this as a multiple choice quiz, you've got to be ready to recognize the different answers. But if you're drawing it yourself, you can set this top carbon here as number 1, or really any of them as number 1. But let's say we set this carbon here as our number 1 carbon. Okay, and let's say we of course have the option to go clockwise or counterclockwise. So let's say we go clockwise. So that's number 1, number 2, number 3, 4, 5, 6. Okay, so at our number 1 carbon we have a tert-butyl group. So I'm going to draw my tert-butyl group, which kind of looks like that. Okay, I've got 1, 2, 3, and this of course is the 4th carbon. Okay, at the number 3 position I have a cyclopentyl group. So if that's 1, 2, 3, I'm going to draw my cyclopentyl group, which is just going to be a pentagon attached over there. At my number 2 position, I have an ethyl group. So there's my number 2 position. Ethyl tells us we have 2 carbons, so it's 1, 2 carbons branching off. At the number 4 position, I have a methyl group. So 1, 2, 3, 4. So here's my number 4 position, and my methyl group would have just 1 carbon. So I draw that single carbon-carbon bond, and there's my molecule. I've accounted for all of the substituents in this molecule. I'm done with that structure. So again, the answer side might have this drawn in a slightly different orientation, but that's okay. All right. It looks like they did use isopropyl in the actual answer key, but like I said, if you don't want to use isopropyl and you want to use the IUPAC name, I think I would have put 5 1-methyl ethyl. I'd probably put that in here between the dimethyl and nonane. Okay, and yeah, you can see here they've drawn the molecule kind of rotated about 120 degrees or so. Okay, now we've looked at cyclic compounds where you have your carbon chain in a ring. It's possible to have more than one ring. We call these fused ring systems or bicyclic systems, bicyclic compounds. Okay, bicyclic means there are 2 rings. It's possible to have more than 2 rings, but a bicyclic compound's probably as complex as you're going to see it. Okay, so for example, here we have if we looked at this molecule here, we could follow a ring. This is just 2 ways of drawing the same molecule, but you could look at it this way, where there is a ring that has 1, 2, 3, 4, 5 carbons. Okay, so that's the sort of pentagon you're looking at over here. You could also see it as a pentagon going this way, right? 1, 2, 3, 4, 5 carbons that way. Okay, so it's kind of this structure. Or you could see a ring as having 6 carbons on the outside. Okay, so it's 1, 2, 3, 4, 5, 6. So that's a hexagon right there. Okay, so even though it's like 2 rings kind of fused together, in a way it's kind of, you could think of it as having 3 bridges at a bridge head. So these 2 carbons here have 3 carbon-carbon bonds coming off of them. Okay, we call that a bridge head, and we have little carbon bridges, connecting the bridge head in various ways. We have a 2 carbon bridge over here, we have a 1 carbon bridge over here, and a 2 carbon bridge over here. Okay, so if we're connecting this way, it's 2 carbons, this way it's 1 carbon, and this way is another 2 carbons. Okay? All right, so how do we name these bicyclic compounds? Well, we start off by using the naming system that we use for cyclic compounds in general. We count the total number of carbons in the system. Okay, so not counting any branches or substituents, but we treat this as one system, and we add, use the appropriate prefix for it and add the word cyclo before it. So in the compounds down here, if we count our total number of carbons, we have 1, 2, 3, 4, 5, 6, 7 carbons. So this would be, we add the prefix bi there because it's a fused ring system, so it's bicycloheptane. Hept referring to the 7 carbons, and bicyclo referring to the fact that it has multiple bridges. Okay, this example up here has also 7 carbons, so this would also be a bicycloheptane of one sort. Okay, now these 2 are actually 2 different molecules. Okay, even though they're both bicycloheptane, okay, you notice that they're not the same molecule. Okay, and you can tell this, if you're having trouble seeing this, try counting the number of carbons in your bridges. Okay, so if I look at this molecule on the left, like both of these are bicycloheptanes because they have 7 carbons, but if we look at our 2 bridgeheads, right, and look at the bridges connecting them, this bridge over here has 3 carbons, this bridge over here has 1 carbon, and this bridge over here has 1 carbon. Okay, if I connect my 2 bridgeheads. Now, if I look at the bridgeheads here on this bicycloheptane, I have a 2-carbon bridge, I have a 1-carbon bridge, and I have another 2-carbon bridge. Okay, so this molecule drawn here is the same one as up here, by the way. Okay, so that's how you can tell that these are 2 different molecules. Now, we have to reflect this in the naming of these compounds. Okay, all you do is you list out the lengths of each of these bridges in descending order. Okay, and you separate them out with periods. So it looks like this. All right, so we would call this bicyclo 3,1,1 heptane. So we put the 3,1,1 separated with periods in square brackets right before heptane. Likewise here, this is bicyclo 2,2,1 heptane, because again we have a 2, 2, and 1 bridge. Okay, so notice that we go in decreasing order of bridge length. Okay, so that's how you name the parent chain, so to speak, of your bicyclic system. Now, you can still have substituents on this, just like you could on any other alkane. And so how you name them is kind of the same thing. You want to add, just list your substituents in alphabetical order and assign a locant to them. Now, how do we assign locants in our bicyclic compound? Well, you want to number your you want to start at one of your bridgeheads, and you want to go through your longest bridge first, then your next longest, and then your smallest, right? Now, of course, you have options oftentimes on which end to start on, which bridgehead do you start from. You want to try and start from the end that winds up giving you a smaller number for your substituents. Okay, so basically, in this example here, we start off with we have our 3-carbon bridge, a 2-carbon bridge, and a 1-carbon bridge. So we start off with one bridgehead, and we number through the longest bridge. So 1, 2, 3, 4, 5, going to the second bridgehead. Then we're going to go through the second bridge. So continuing from there, there's 6, 7. Okay. And then the last bridge has that 8th carbon. Okay. So likewise, with here, if we've got 2 options for which bridgehead we start from, we could start from this bridgehead and go, around this way, or start from this bridgehead and go around this way. This method is better because it gives us a lower number for our substituent with our methyl group here. For this one, where that methyl group is on this number 8 carbon, it doesn't matter which way we number it, it's still going to be on that number 8 carbon, so it's kind of a moot point. But here, which side we start from makes a difference, and that's why we want to go with the 6-methyl bicyclo 3,2,1 octane. Cyclooctane, I should say. Right. All right. So the rules we've gone through are relatively straightforward, and with the smaller molecules that we typically use, they give us really easy to follow names. Obviously, this gets a little bit more complicated as you start dealing with larger and larger molecules. So especially once you start getting to some biomolecules or things in pharmaceuticals, we're dealing with some complex naming, right? This is where common names kind of come in. Okay, so for example, here we have the pharmaceutical Nexium, right? Also, generically known as esomeprazole. Or esomeprazole? I'm not sure how that's pronounced, but anyway, my point here is that you could write an IUPAC name for it, but it's going to be pretty complicated because it's such a big molecule with so many different functional groups. That's why, you have a common name to make it easier to refer to and to market. All right, so let's talk a little bit about constitutional isomers. I kind of alluded to this earlier when I pointed out, why we take this very systematic approach to naming things. All right, I think I used an example of 3-methylpentane and 2-methylpentane and pointed out that you need to be able to distinguish between them and that's why the naming system has to take that into account. That's why we have to have different names for those two compounds, because they are not identical. Okay, so isomers, just to jog your memories, isomers are two molecules that have the same molecular formula but different structural formulas. Okay, they're different somehow. You're able to distinguish them. So if you can do this in the in a manner of the way things are connected, we call these constitutional isomers. Okay, so there's a difference in connectivity when it comes to constitutional isomers. So let's look at hexane, for example. All right, so here both of these molecules have the formula C6H14, but clearly they're different molecules. This molecule has 1, 2, 3, 4, 5, 6 carbons connected in a string, and so that is just hexane. This molecule has 1, 2, 3, 4, 5 carbons in its parent chain, and it has a methyl group branching off the number 2 carbon. So this would be 2-methylpentane. Okay? So even though these both have the same molecular formula, they are isomers of each other with different structures. Now notice that because they are different molecules, they have different names, right? So notice that we named this molecule here on the left as hexane, and this molecule on the right as 2-methylpentane. So I'm pointing this out because this is actually a really good tool for determining whether a molecule you've drawn is identical to another molecule, or if you've drawn a different isomer. Okay. When in doubt, name your molecule. Writing out the name is kind of a surefire way to determine whether two molecules are identical or isomers. Okay, this would be a good exercise if you try doing this problem here. Try drawing the remaining 3 constitutional isomers that you can draw for hexane, or draw for C6H14. Okay, so obviously you've drawn this, but the reason I'm pointing this out is that sometimes you draw a molecule thinking it's different, and it's not. So for example, you might draw one isomer. You say, okay, well, if I start off with a pentane as my root word, and I have one of my methyl groups branching off here, could I just move that methyl group and make a new isomer? So for example, instead of having that methyl group at this number 2 position, could I have this methyl group over here? Yeah, you could. Okay, and this is 3-methylheptane, or 3-methylpentane, sorry. And that is why it is a different isomer. Now you might say, oh, let's just keep doing that. Let's move this methyl group over here. Now that's a new molecule, right? That looks different, right? But if you start naming this, right? If you say like, oh, this molecule looks different from all the other ones I've drawn, and therefore this is a new isomer, try naming this guy, and you'll see why this is not an isomer. Because remember, we want to start numbering from the right because that's closer to this methyl group. So that's 1, 2, 3, 4, 5 carbons. This is at that number 2 position. This is 2-methylpentane. And you've already drawn 2-methylpentane. Now, at this point, you might realize, oh, this molecule is just this molecule rotated 180 degrees. I've just flipped it over. Okay, and that's why these two are the same molecule. So this doesn't count as a new isomer. Okay, this is the same thing as that. All right, so you've got to be a little bit more creative. Likewise, you might be tempted to put a methyl group on either this carbon or this carbon, and you'd quickly realize, wait a minute, I've just drawn hexane again. Okay, so you want to draw other isomers, and they'll have different names. Okay. At this point, I think we've exhausted. Oh no, actually, yeah, we have. We've exhausted all of the methylpentane derivatives. So you might want to try maybe starting with a butane as a root. Okay, so feel free to pause this if you want to try drawing the two other potential isomers for this molecule. Okay, and so here they are. These are the two other molecules you hopefully drew. You may not have drawn them exactly like this. You may have drawn them like rotated or somehow just oriented a little bit differently. But if you try naming them, you'll realize that you've got at least these two names. This one is 2,3-dimethyl butane. Okay, I can tell because I've got 1, 2, 3, 4 carbons, so that's the butane root, and I've got methyl groups on the 2 and 3 positions, so it's 2,3-dimethyl because there's two methyl groups. Here we have 1, 2, 3, 4, so again this is a butane root. I've got two methyl groups on that number 2 carbon. It's number 2 because remember we've got to start numbering from this end that's closer to it. So this would be 2,2-dimethyl butane. Okay. Please note, by the way, that even though both methyl groups are on the same carbon, I still have to have a substituent for each of them. So I have to write 2,2. You can't just say 2-dimethylbutane. That's a little ambiguous. You have to have a locant for both those methyl groups, even if that locant happens to be the same number. Okay? So 2,2-dimethylbutane. And again, that's how you can tell that these are 5 different isomers. If you at any point got the same name for something that you'd already written down, you'd quickly realize, hopefully, that you just drew the same molecule, just drew it in a different, conformation. All right. As you can see, like the number of carbons you have to play around with greatly increases the number of possibilities. So don't panic if you ever get a question that asks you to draw all the potential isomers of something. It'll probably something closer to this end. You're not going to be asked to draw, all the potential isomers for something that has 40 carbons, for example. That'd be ridiculous. But my point here is that the numbers do increase as you have more carbons to play around with. Okay, so this is something I've kind of alluded to. How do you tell if you've got two molecules and you're not sure if they're isomers or the same molecule just drawn differently? There's more than one way. I obviously showed you the foolproof method of just naming them, right? You could quickly name these two molecules and discover, wait, these are both 3-methylpentane. They're identical molecules. One thing I want you to try to get better at, and this is an acquired skill. It takes a while to get a hang of this, so you're not going to be good at it immediately, and this is why you need to practice it, is to try to be able to manipulate things in 3D. Now, eventually you can get to the point where you can do this mentally. You can look at a molecule and mentally rotate around those bonds and figure out, oh, this is the same molecule. It's just rotated, 90 degrees, and this bond over here is rotated 180 degrees. I can look at that and see that, but you probably wouldn't be able to do that. Okay, what makes this a little bit easier is working with a 3D model. So if you build a model of this molecule and start twisting around around these carbon-carbon bonds, you can recreate you can recreate the other version of this molecule and sort of prove like, oh, these are the same thing. Okay, but like I said, without a model kit in front of you, the option is to also just name them. Oh, speaking of which, you are entitled to use a model kit on any quiz or exam. So like a periodic table, you are allowed to have a model kit with you when you have a quiz or exam. I highly recommend you keeping a model kit with you when you're doing your homework, and just get comfortable with it, because like I said, the more you sort of play around with these things and you manipulate the model and start getting a feel for its 3D structure, that's when you start internalizing it in your brain. Your brain starts thinking in 3D more, and then you're able to do this more mentally rather than needing the model. But using a model is kind of a key stepping stone there. So if you haven't bought a model kit yet, I highly encourage you to get one. It will really make trying to understand how to think in 3D a lot easier. Okay, so when I said you rotate this and then flip one of the bonds, I was able to look at this and figure that out. Here's what I was talking about. Okay, so here they actually did the bond rotation. I think it looks like they're doing this backwards. They took the second molecule, so they rotated this bond over here 180 degrees. Okay, so this basically flips over, right? And then they rotate this molecule slightly counterclockwise. And there you can see it's what happens when they've rotated that way. Okay, so if you're having trouble seeing what I'm saying here, so basically they took this, they rotated this bond over here. Okay, and that's what got this to point downwards. So I say 180 degrees, but you know, I'm kind of like flipping it over. Really, it's actually like 120 degrees or so. And then they just took this whole molecule and just rotated it, you know, and that's kind of how they got this, you know, the original molecule we started with. Though, of course, as I pointed out, you could just number and name this, right? So you look at your longest carbon chain, it's got 5 carbons, so it's got that pentane root. The methyl group that's branching off is at that number 3 carbon for both of them, so they both have the name 3-methylpentane. Okay, so either way, like, you know, you're kind of guaranteed to figure out which one, that, you know, that both of these are the same molecule. So, like I said, I think naming it is probably the more foolproof of the methods. Okay, so let's talk a little bit about the stability of various isomers. Okay, typically when we talk about stability, all right, that in physics and in nature in general, things seek out the lowest energy. So the more stable a molecule is, the lower its potential energy. Okay, so that's something to keep in mind, all right, that things that are more stable are at lower potential energy. As a result, when they react, they give off or produce less energy. Okay, so it's you know, so typically that's something to keep in mind, because we can use that to our advantage when trying to determine the relative stability of molecules. Okay, one way we can do this, we can figure this out, is to do a combustion reaction and observe how much heat is given out in that combustion reaction. Okay, because when you have a combustion reaction, you react your hydrocarbon with oxygen, and your products are carbon dioxide and water vapor. These are very stable molecules that have very low potential energy. By looking at the amount of energy that's given off, that's released when you make these products, you can figure out how stable your initial hydrocarbons were. If they were very stable, you would get relatively less energy. If they were very unstable, you get relatively more energy. So if you're having trouble visualizing that, here's a kind of a graph representing that. Okay, so you can see here that as we introduce branching to these 3 isomers of octane, you can see that the more branched our isomer is, the more stable it is potential energy wise, and therefore it releases less energy. Okay, all of these reactions are exothermic, don't get me wrong, all of these release a lot of energy, but by comparing the relative amounts of energy, you can see that our straight chain version releases more energy than our highly branched version. Okay, and by comparing the energy gaps, we can assign an energetic value to the difference in stability between our different isomers. We can say that this branched isomer is 18 kilojoules more stable than this non-branched one, the straight chain one. Okay, so we've talked a lot about alkanes and how we name them. Let's talk a little bit about where they come from and some of their physical properties. Okay, you've probably heard of the word petroleum. I think it's more common in British English than in American English. But petroleum is another word for crude oil. Okay, the word petroleum, like petros means rock, and oleum refers to oil. So it's this that's the source of alkanes, and really like most hydrocarbons. What you do is you refine it by essentially doing fractional distillation, right? You can boil, like, slowly boil off the different fractions, the different components of your mixture and separate them out. Okay, it's very similar to the distillation experiment we did in lab, but you know, obviously we're dealing with lots and lots of fractions that are really close in boiling point here. Okay. So we kind of separate our mixture of crude oil, of our petroleum, into our various fractions, which have different lengths of carbons, okay, and therefore grouped together with similar boiling points. So the the very small carbon chain, so if you have a carbon chain between 1 and 4 carbons, these are gases at room temperature. So these tend to be things like natural gas and things that are like used for like include things like propane, butane. You can have further refinement to try and separate this out further into like propane versus butane versus like methane and so on. All right. Once we start getting to like between 5 and 12 carbons, now we're getting into that octane range. So that octane's kind of in the middle of this with 8 carbons. That's kind of what we like to use for gasoline, for fueling cars and things like that, and personal vehicles, and things like lawnmowers and stuff. Once you start getting into longer chain carbons, now these are higher energy and used for heating, for fueling airplanes and ships and things like that. I guess really heating oil is actually even longer chain than that. Um, you know, as you start getting into higher and higher carbon chains, now you're going from liquids to things that are getting a little bit more viscous and eventually more solid. Now we're getting to things like asphalt and tar, things that are used for paving roads and keeping them relatively waterproof. Okay, so basically, that's kind of how we split up our crude oil. Now, out of these, you probably figure that this fraction over here with gasoline is probably the one you want to utilize a lot. I mean, you probably need a lot of natural gas and stuff like that for fueling certain things, but gasoline is probably the one we churn through the most considering how many vehicles we use. So, if you were to just only get your gasoline from fractional distillation of crude oil, you wouldn't get enough. So we need to do more. We need to take some of these longer chain hydrocarbons, and then basically crack them. We break them apart into more useful, smaller fractions. Okay, so things like gasoline and so on. Okay, so cracking is just the process by which we break down these larger hydrocarbons into smaller hydrocarbons that are, just more useful. Okay, so one way to do this is to heat up your alkanes with hydrogen at a high pressure and temperature, and that causes spontaneously break apart. We can take branched alkanes and produce them from straight chain alkanes or vice versa. This process is called reforming. That's where you're sort of just converting one form of an alkane into a similarly sized alkane, just a different level of branching. Okay, whereas cracking is where you take a longer hydrocarbon, break it down to smaller pieces. Reforming usually involves roughly the same size hydrocarbons. Okay, and that thereby you increase your yield of gasoline. All right. So so as I pointed out, the lower carbon chain ones are gases. You start getting to a liquid range between 5 and 12 carbons. That's a little bit more useful for for things like gasoline and fueling personal vehicles. Once you start getting to larger alkanes, you're starting to get more viscous materials that are still good for like heating oil and stuff like that. And then once you get getting to really large lengths, now you're getting to solids like tar and wax and asphalt and stuff like that. Okay, so you probably notice that as we increase the size of the molecules by adding more and more carbons, our melting and boiling points are increasing, right? We're going to things that have gases where the boiling point is below room temperature, right? So they've boiled into a gas at room temperature, to liquids that have a boiling point that's below that's above room temperature, but a melting point that's below room temperature. Okay, so that's why they're liquid room temperature. And then finally, solids that have a melting point that's above room temperature. Okay, that's why they're still solid at room temperature. Okay, so generally you can see that those intermolecular forces get stronger as you increase the size of your molecule. This should be in keeping with what we saw in GenChem and when we reviewed this in Chapter 1. Remember, your hydrocarbons are relatively non-polar, right? So the only thing they have available to them are London dispersion forces. And while London dispersion forces themselves are weak, the more electron density you have to play around with, the more the effect of London dispersion forces that we see. Okay? And that's why we notice these melting and boiling points increasing as the molecules get bigger. Okay, so let's talk a little bit about how to represent these molecules. Okay, we have that same problem that we saw a couple of chapters ago, where we're trying to represent a 3D molecule on a two-dimensional sheet of paper, right, or two-dimensional screen if you're watching this video. And we have ways around this, right? I think you guys have already seen we could use wedges and dashes to help point out where the atoms are. So if you see a straight line, those bonds are in the plane of the paper, or in this case the screen. A solid wedge means that atom is sticking towards you, so it's sticking out of the plane. And a dashed wedge means that bond, that hydrogen, is sticking away from you, sort of into the plane. Okay, so it's sort of behind the plane, so to speak. All right. That being said, we can have other ways to represent these things in 3D, including the sawhorse and the Newman projection. Okay, with a sawhorse, basically you put this in the most stable sort of staggered conformation here, where you can see. Actually, I guess you don't necessarily have to have it in a staggered conformation, because same with the Newman projection, this is shown in a staggered conformation, but we could have it as eclipsed. I'll explain what I mean by those words in a little bit. But basically, you kind of set it up so that we have our carbon-carbon bond here, and we have one carbon towards us and one carbon away from us, and we show what's connected to those carbons, right? In the case of a Newman projection, it's the same thing. This carbon that's closer to us, okay, is shown over here as this point. Okay, so that's this carbon over here, and it's the same as this carbon if you were looking from the left. So basically, if you had your eye over here, okay, and you were looking down this carbon-carbon bond, this is how you would see these two molecules. So you're looking at that carbon, and that's this point over here. The back carbon over here that's further away from you, or this carbon if you're looking at it using sawhorse, it's represented with this big circle, and you show what's attached to it by what's attached to the outside of the circle. Okay, so notice that front carbon has things attached directly to that point. The back carbon has things attached to the outside of that circle. Okay? So that's kind of what's going on here. You're looking down that carbon-carbon bond, and you're describing things as you see them. Okay? So if you see, this hydrogen here pointing upwards, that's this hydrogen here. You can see these two hydrogens to your left and right respectively pointing kind of downwards. So that's what's going on here. With this back carbon, you have a hydrogen that's pointing downwards, and the top hydrogen is going to the left and right, and that's kind of what we're seeing here, represented with the hydrogens in blue. So that in mind, let's try this out. Okay, so again, using dashes and wedges, we can kind of figure out where these things are pointed. Okay, so feel free to pause this video and see if you can draw a Newman projection for this molecule here. Okay, if you're getting stuck, one thing to start off with is with that general template, right? You want to start off with a circle, okay, for that back carbon. So this circle I'm drawing represents this carbon over here. Now notice that this chlorine is in the plane of the paper and it's above the person's eye. So in other words, we have this chlorine and it's sticking up here. Now, because carbons are sp3 carbons are tetrahedral, we're going to have two groups here and here. And in our central carbon, okay, sorry, the carbon that's closer to us, rather, notice that this methyl group is pointing downwards, right? And that's in the plane of the paper. So that's going to be down here, and we're going to have two other bonds coming off of it here and here. So we're starting off with this general template. So now think about what's been provided to you and how to draw it. Okay, so over here we have that's a methyl group. So I'm just going to, I could just draw it this way, but I could also write CH3 just to remind me that that's a methyl group. Likewise, for this methyl group over here, this bond is pointing away from you. Now, from that observer who's looking this way, is that methyl group on this person's left or right? If it's pointing away from us, it's on that person's left. So you can imagine this person is looking at this bond. This methyl group over here is to that person's left. So in other words, it's this group over here from their point of view, CH3. You could write CH3. I like to write it like this, kind of backwards, just to show that it's the carbon that's attached there. So what are these other atoms? Well, remember, this is a your bond line diagram or a skeletal structure where you don't draw hydrogens. All of these other bonds are to hydrogens, and that's why they don't show up. Okay, so that's kind of what the Newman projection for this molecule looks like. Now, what would this look like if the observer were looking from the opposite direction? So if their eye was over here, right, and they were looking this way, what would that view look like? Okay, so go ahead and take a second and try and draw that out. Okay, so if you were drawing that out, again, you start off with a circle. Now, from their point of view, it's the carbon that's closer to them that has that chlorine pointing upwards. So chlorine up here. I have two groups to my left and right. In this case, again, that methyl group is pointing away from us, so it's to this observer's right. So this is that CH3 group that's over here. Likewise, this group's pointing, and the back carbon's away from them. That's our CH3 group. And all of our other bonds are to hydrogens. Okay? So you can see how this is kind of, you're kind of flipping which is your front and back carbon, and you're kind of reflecting both of these in kind of a mirror image. So this methyl group, instead of being on the left, is now on the right, and it's on the atom that's closer to you. Okay, so here's that molecule drawn here. Okay, so they haven't written CH3, they've just drawn a line representing carbon bond, but it's understood that there's a CH3 group over here. Okay, so let's talk a little bit about the angles between groups on adjacent atoms. Now, normally when you think of bond angles, you think of angles between two bonds that are connected by a mutual atom. Here, this isn't the case. Here we're looking at angles between groups that are on adjacent atoms. There's an extra bond in between the two bonds that we're comparing here. Okay, so that being said, the angle between these groups is kind of important when we're trying to determine the stability of a particular conformation of a molecule. Okay, so we call this this angle the torsional angle, or the dihedral angle, and any strain, any sort of repulsion caused by the the bulkiness of the groups involved here, that's known as dihedral strain or torsional strain. And this is one of those driving forces that affects the stability of the molecules we're looking at. Okay, so how do we measure this? Again, pick two atoms that are on adjacent carbons. So if we pick this hydrogen that's on our front carbon, and we pick this hydrogen that's on our back carbon, so two atoms that are sort of next to each other like this, you can then measure the angle between them. And this is a 60-degree angle. Okay, so we say that's, a dihedral angle of 60 degrees. Okay, you could also you could use a protractor to measure this angle, or you could kind of figure out that you've got 360 degrees and there are 6 little segments like that when you take into account the 3 atoms that are coming off each of your carbons. So 360 divided by 6 is 60 degrees. So that's another way to figure it out. Okay, so when you have the 60-degree torsional angle, we call this a staggered conformation. Okay, it's staggered because we don't have any overlap between atoms on adjacent carbons. Okay, and because of this lack of overlap and therefore less steric hindrance from that, less repulsion between those groups being sort of stacked on top of each other, they're lower in potential energy. They're more stable. Okay. Alternatively, we can have what's called an eclipsed conformation, where your hydrogens are your bonds are kind of overlapping. Okay. Here, your dihedral angle is actually 0, but it's drawn slightly off just to make it a little bit easier to see the groups that are that back carbon. Okay, because otherwise, if they were completely overlapping, it would be hard to read what was what. Okay, so how does stability or potential energy change as you rotate around a carbon-carbon bond? You can see that you can go from one staggered conformation to another. If we take 2 hydrogens and highlight them in red to show you how this is changing. Okay, so if we rotate this, 120 degrees so that this hydrogen is pointing down here. Okay, notice that we could rotate another 120 degrees so the hydrogen is pointing here. And then, of course, another 180 degrees puts these 2 hydrogens across from each other, okay, which is the same way as you started with. Okay. Likewise, in between that, as you're rotating 60 degrees, you have to go through this eclipsed conformation, this eclipsed sort of intermediate. And notice the jump in potential energy, because now you have this repulsion between these groups. They're kind of overlapping each other and repelling each other a little bit, and that makes the molecule more unstable and therefore increases its potential energy. Now, if you wanted to calculate how do I quantify this strain? How much of a strain does each of these interactions cause? Well, if I go back, you'll notice that there's a 12 kilojoule energy gap between our unstable conformer and our more stable conformers, right? So since there are 3 of these steric interactions, that basically averages to about 4 kilojoules per, per pair of hydrogens, per, set of steric interaction here. Okay. So you can explain this in multiple methods. You can kind of explain this using just the repulsion of the electron clouds in your hydrogens. You can kind of explain it a little bit using molecular theory as well. Okay, it's basically when you have a staggered conformation, the slight overlap of orbitals yields a little bit of stability. Okay, it helps sort of delocalize that electron density a little bit. Okay, even though there's an antibonding orbital, molecular orbital involved here, that's not the same thing as saying you're donating electrons into that orbital. Okay, you're not putting electrons into that antibonding orbital. That would break the bond, right? That would destabilize the bond. Instead, you're just using just kind of this sort of interaction, this sort of weak attraction between the 2 orbitals, that weak overlap, and that helps lower the potential energy, makes it a little bit more stable. Now, what if we have groups other than hydrogens that are attached to our carbons? Okay, how does this affect the torsional strain we're seeing, right? Potential energy. So here you can see that the difference in energy increases. Our our eclipse conformations with this bulkier methyl group start getting more, more higher in potential energy, right? So there's more of a, instability due to the bulkiness of this methyl group affect, sort of repelling the electron density around the hydrogen. Okay, so if you wanted to figure out the increase in that effect, that extra 2 kilojoules can be accounted for by having that larger methyl group there instead of a hydrogen. Okay, so it's 6 kilojoules per mole instead of 4 kilojoules for a hydrogen torsional strain. What if you have 2 bulky methyl groups? Now, this is interesting because it kind of changes the profile a little bit, right? We've seen the interaction between methyl groups and hydrogens in the previous example, but what if we have 2 methyl groups interacting with each other? Well, then the strain's even greater. Okay, we have a strain of 19 kilojoules per mole. Okay. Likewise, the stability of having our 2 methyl groups across from each other is much better than where they are at 60 degrees to each other. Okay, so notice that this conformation, what we call an anti-conformation, where our 2 methyl groups are across from each other, are lower in energy than these conformations where they are 60 degrees from each other, what we call a gauche interaction. So let's talk about some of those names. I pointed out that if you have a staggered conformation, if you have your 2 bulky groups across from each other, okay, at 180 degrees, we call that an anti-conformation. Anti-conformations are the most stable, okay, that have the lowest potential energy because you have these bulky groups so far apart from each other. There's less steric hindrance, okay, between them. They can't repel each other as much. A gauche interaction, like I said, is when you have a 60-degree angle as opposed to 180 degrees. Okay, so you have a 60-degree angle between your 2 groups, and this can be on either side, of course. So that's a gauche interaction. That's a gauche interaction. Okay, and gauche here, by the way, is spelled G-A-U-C-H-E. Okay, and just like with our methyl group and hydrogen, you can calculate what is the value of this torsional strain by just doing a quick, math calculation and subtracting what we know. We know this hydrogen-hydrogen interaction is about 4 kilojoules per mole. So if we subtract those interactions from, the total energy difference, we can then figure out where the strain for just that methyl group interaction comes from, and figure that out accordingly. All right, so just plugging that in, just from the last few examples we've got, we can kind of see as we increase the size of groups that eclipsed, and we compare an eclipse conformation, versus a gauche staggered conformation, we can see how the energy cost changes accordingly. We can see that the largest energy cost comes from having bulkier groups in that eclipsed interaction. Okay, having 2 small groups isn't too bad, but even that's worse than having a gauche interaction. So you can see an eclipsed interaction is way worse than even just 2 bulkier groups having a gauche interaction. Okay. All right, let's practice this out. So go ahead and try drawing a Newman projection for this molecule. Okay, so I recommend first trying to draw the molecule, and then look at carbons 3 and 4, and imagine that you're looking down that axis. Okay, so if you can pause this video and try that out, but if you are having trouble seeing that, let's draw that molecule out really briefly. So we've got hexane as our root word there. Okay, so we're going to have 1, 2, 3, 4, 5, 6 carbons. It's 2,2,3,4,4 pentamethylhexane. So we've got 2 methyl groups on that number 2 carbon. So if we number this 1, 2, 3, 4, 5, 6. So we have 2 methyl groups on that number 2 carbon, hence the 2, 2. We have 1 methyl group on the number 3 carbon, because there's only a 3 listed there, so that's down that way. And we have 2 methyl groups on that number 4 carbon. That's why 4 is listed twice. Okay, and carbons 1, 5, and 6 don't have any other substituents. Okay, we want to look down the axis of carbons 3 and 4. So that's these 2 carbons here. So you want to picture, your eye looking down that bond. Okay, so take a second again if you want to pause the video and see if you can draw it now based on this diagram. Okay, so carbon number 4 is going to be your back carbon, so remember, represent that with a circle. Okay, and then you've got this carbon over here, that's your front carbon. Think about what's on that carbon, right? You've got a methyl group and a tert-butyl group, essentially. And what's not shown is that there's a hydrogen on this as well. Okay, so if that front carbon, we have a methyl group, we have a hydrogen, and we have our tert-butyl group. Okay, and on that back carbon, we have 1 methyl group, another methyl group, and we have an ethyl group, essentially. Okay, so we have, so if I draw it this way, an ethyl group, and here are my 2 methyl groups. That's basically what that looks like in a staggered conformation. Okay, now we need to draw the highest and lowest energy conformations. Now, how do we draw the how do we start going about solving this problem, right? Well, probably be easier to draw the lowest energy conformation first. Actually, I think I may have drawn that just naturally here. But basically, if you want to draw your lowest energy conformation, first of all, you need to have it staggered, like we've drawn here. Okay, you want to have this staggered conformation, just because if you have an eclipse, that will naturally yield the highest energy conformation. So for the lowest energy conformation, you probably want your bulkiest groups away from each other, which again seems to be what we've done. We've got this tert-butyl group on our front carbon, okay, and it's at 180 degrees. It's anti to this ethyl group, okay? So this is actually probably our lowest energy conformation. Okay, our largest groups are anti to each other. You're obviously going to have some gauche interactions here, but those can't be helped, all right? Now, if you want to draw your highest energy conformation, your least stable one, you want to do the opposite. You want to have your 2 large groups on each of your carbons eclipsing each other. Okay, so you would then rotate this so that this ethyl group is eclipsing, or rather this tert-butyl group is eclipsing this ethyl group. And when you rotate this so that's set up, this methyl group comes down here and eclipses with this methyl group. And this methyl group over here is eclipsed by this hydrogen. Okay, so on my next page, here are the, here's what that lowest energy conformation looks like. I drew one enantiomer of this, so to speak. We'll learn about enantiomers in a different, in a later chapter. But basically, you may have drawn the mirror image of this molecule, and that's okay, is what I'm getting at. Here's what that eclipsed conformation looks like, and you can see it's a little messy, but the bottom line is you can see how that tert-butyl group and ethyl group are overlapping, a methyl group and a hydrogen are overlapping, and 2 methyl groups are overlapping there. Okay, so whichever way you drew it, that's kind of how it's the highest energy conformation. Okay. While we're talking about torsional strain, okay, the sort of the physical placement of these groups causing some instability, we have to also see this effect in cyclic compounds. Cyclic compounds aren't immune to this. In fact, it's kind of worse for them because they're kind of locked into place because of their ring structure. Okay, so we can have what's called an angle strain or a bond strain because the bond angle of your cyclic alkanes are kind of locked into place just geometrically, right? So, for example, if you have cyclopropane, right, those three carbons are connected in a triangle. Well, what is the bond angle in an equilateral triangle? It's 60 degrees. But how does that compare to the bond angle for an sp3 carbon? Remember, sp3 carbons want to be tetrahedral and have a bond angle of 109.5 degrees. So 109.5 degrees versus 60 degrees is a pretty significant difference. So it turns out that cyclopropane is actually a very unstable molecule as a result due to this bond strain, okay, that angle strain. Likewise, here we have cyclobutane with, it's a square, and so you think that it would want to be a 90-degree angle. Some of these molecules get around this ring strain by not being flat. We get kind of a puckered structure to these molecules, and that helps alleviate some of this ring strain. Okay, it turns out that cyclopentane and cyclohexane are very stable when it comes to cyclic compounds. So you'll see that, especially cyclohexane, I think, is one of the more common cyclic alkane systems you're going to come across. Okay, so you can see here that sort of relative stability, that comes about in that cyclohexane range. Okay, you can see that as a lower relative heat of combustion compared to all the others. Okay, so yeah, and this is kind of showing why the size of your ring, if it deviates either too small or too large, you start building in this ring strain, right? This bond angle strain, due to your angle being forced too small, or in this case, too large. So too acute an angle, and here too obtuse an angle. Okay, once you start getting to larger rings. Okay. I think this is kind of illustrating again that issue that we saw with sp3 hybridized carbons, right? That angle wants to be 109.5, but a triangle needs that angle to be about 60. And you can see there's some issues there with trying to get the overlap between those sp3 orbitals to make sigma bonds. You need to have a direct overlap. It's hard to get a direct overlap with that bond angle. Okay. The other thing that's interesting here that you don't see just from that ring strain alone is there's still torsional strain here. Oops. There's still torsional strain between those carbon-hydrogen bonds, okay, on adjacent carbons. Okay, you can see we have a little bit where, since we're kind of locked into this structure, there's a bit of an eclipsing here between those carbon-hydrogen bonds. Okay. As I pointed out, once you get to more than 3 carbons, though, you can try to alleviate some of this strain by hopefully doing what's called puckering. You can bend the molecule, and that kind of like minimizes the negative effects of this angle strain and torsional strain. Okay, so here we've got cyclopentane. You can see it's significantly more stable than cyclopropane and cyclobutane, right? We're much closer to the accepted value. You still have a little bit of puckering to minimize energy here. So even though the bond angle of a pentagon is relatively similar to 109.5, it's relatively close. There's still a little bit of puckering here. You kind of have what's called an envelope conformation. You have one carbon kind of sticking up like the flap of an envelope, and that's kind of gets rid of that little bit of ring strain. You have a lot of torsional strain too, of course, since you've got some overlap with these carbon-hydrogen bonds. So if this carbon were the same plane as all the others, its hydrogens would overlap with these ones adjacent to it. So having it stick up a little bit kind of gets rid of some of that torsional strain as well. Okay, so cyclohexane, as I pointed out, has no ring strain because of the way it sort of puckers itself to get rid of that strain. Okay, so you get this sort of puckered structure where you have carbon atoms alternating up and down. Okay, and that kind of gets rid of torsional strain. Right, it's only every other carbon that has you know what's it that has these bonds that are kind of parallel to each other or eclipsing each other, which you could have some strain there with bulky enough groups, but these hydrogens are a little too far apart to really affect each other too badly. Okay. Um, Also, you don't have to worry too much about these bond angles. They're kind of close to 109.5 degrees. They're not locked into the geometric angle that you see in a hexagon because of this puckering. Now, this is called a chair conformation. This is the most stable conformation of a cyclohexane. You can have other conformations, but in those you don't have, you're going to have some torsional strain with those. And as a result, those are going to be slightly less stable. Okay, the chair conformation is the one that has zero torsional strain and zero angle strain, to kind of make it very stable as a result. Okay. So yeah, if you're having trouble seeing why this is a chair, building this model helps. Also slightly rotating this, but basically if you rotate this so this end over here comes up a little bit, that's kind of like the back of the chair. This is the seat. Okay, these four carbons here kind of make the seat of the chair, and this is kind of like a footrest. Think of it that way. Okay, so yeah, so when you think of it as a chair, don't think of it necessarily as a dining chair. Think of it more like a deck chair, um, like a chair you'd see like by a pool. Okay, so here you can see we have a boat conformation. So like I said, there are other conformations of hexane that exist but are less stable. So the boat has, instead of having one of these ends pointing downwards to make the chair, it also points up. So you have both of your two ends of your cyclohexane pointing upwards. Okay. Yeah. As a result, also notice that you have some a little bit of steric hindrance. Again, here we have relatively small groups, but notice that they are pointing towards each other. Okay, so if you want to compare the stability of these, if you build a model of cyclohexane and you're trying to twist it from one chair conformation to another, basically, as you go through it, you'll see you can probably see a little bit better how the interactions yield more stable or less stable, interactions. So, for example, you kind of bend down. So as you take this part that's bending down over here, and you kind of start to bend it upwards, you're trying to get it to that boat conformation. In between there, you get this half chair conformation. Notice that all of these carbons are in the same plane, right? So there's going to be some torsional strain there as well as some ring strain there, okay, in those bond angles. So that's why this has such a high energy conformation. If we tried doing that from the other end, if we tried raising this part here, it does the same thing. There's a little island of stability on the way there called a twist boat. You have less, a little less torsional strain because these are no longer in the same plane like they are in the boat. So that's why this is slightly more stable. But again, the chair conformation is definitely the most stable conformation for this molecule. So, how to draw a chair? Okay, I recommend doing this a little mindlessly just to make it kind of second nature. Just try drawing chair conformations. Essentially, you have three sets of parallel lines, and so they kind of look like a little bit like the bow tie type picture. I use the Budweiser logo here for comparison, but it kind of looks like that. It kind of looks a little bit like a bow tie, but quick way to tell that you're doing it correctly is that there are three sets of parallel lines as drawn here. Okay. Now, when you're drawing substituents on each of these carbons, your what are called axial carbons, the ones that are pointing straight up or straight down, okay, have to be attached to they continue on in the same direction as the carbons they're attached to. So in other words, the carbon, so the attachment that's pointing upwards, okay, on a carbon that's upwards will be axial like this. It'll be kind of straight up like this. If you have a carbon that's pointing downwards and you have an attachment that's also pointing downwards on that, that's also pointing straight down. Okay? Now, I call these axial, and that's to denote that they are different from what we call equatorial carbons. Okay, so an equatorial carbon are the ones that are kind of parallel to our parallel sets of lines, and they're called equatorial because they're kind of in that, roughly in the plane of the equator of this this ring that we form from our cyclohexane. Okay, there's kind of in roughly the same plane, as opposed to the axial ones that are kind of perpendicular to the plane. So if you imagine that this was kind of like a ring or a globe, and it would spin on an axis, your axial ones are kind of perpendicular to that axis, whereas your equatorial ones are kind of perpendicular to the equator of that spinning cyclohexane. Okay. So here are all the attachments to each of those carbons. Because remember, all of those carbons would form 4 bonds, so they have to have 2 substituents. You know, when you don't count the bonds used to form the ring. Okay. So yeah, so notice that if you want to figure out if something's axial or equatorial, as I kind of pointed out in the previous slide, look at the the carbons attached to it and determine, is it pointing upwards or downwards? So up, down, up, down, up, down. You can kind of get a feel for that. If a group on an up carbon is also pointing upwards, it's axial. If a group on a down carbon is also pointing downwards, it's axial. Okay, so like up, up, or down, down. Okay. Likewise, if the groups are opposite from their carbon they're attached to, so an up carbon but a down group is equatorial. A down carbon but with an up group is also equatorial. Okay, so you can see that here, like as well. Down group, there's a down carbon, but this is an upward pointing group. Okay. All right. So something to keep in mind. So when you have substituents on your cyclohexane, so one of these groups is swapped out for, or so one of the hydrogens on your carbons is swapped out for something else, all right, something that's not a hydrogen. Where it's located actually changes depending on how your chair flips. Okay, so remember, your chair conformation doesn't have to stay static. It can flip into a boat conformation and then flip into the other chair. Okay, so this set of carbons that's pointing downwards can then start pointing upwards, and this one that's upwards can start pointing downwards. Okay, and of course it goes through a kind of a boat intermediate. But notice that when this carbon's upwards, and this group that's upwards on it will be axial, right? Remember, up, up, it's axial. When we do a ring flip, this carbon is pointing downwards now, as you can see, but this group that is still attached to it, upwards. So if it's a down carbon but an up group, remember, down, up is equatorial. So notice that we went from an axial group here to an equatorial group here. Okay, so that's something to keep in mind, that doing a ring flip switches your substituents from axial to equatorial and equatorial to axial. Okay? So that's something to keep in mind. Right? It turns out that equatorial groups are generally, that's a generally more stable place, especially if you're trying to put a bulky group away, from other atoms. Okay? Even though we have a bit of a gap here, a bit of a space between one axial group and another, right? Because they're 2 carbons away. There's still sometimes some strain here, especially depending on how bulky that group is. Okay, so having it at that equatorial position where it's pointing away from everything might be a little bit more stable. Okay, So you can see that here with an example of methyl cyclohexane. If we were to compare the relative population of our different conformations, it turns out you get way more of this conformation where the methyl group is equatorial, as opposed to this one where the ring flip has it in the axial position. Only 5% has it in that axial position. Okay? So if you want to see that, this is where that strain comes in. So even though there's 2 carbons away, these axial groups are 2 carbons away, there's still some strain there because of the bulkiness of this group. We call this a 1,3 diaxial strain. 1,3 because, again, if you count this as your number 1 carbon, this is your number 2 carbon, this is your number 3 carbon. So it's the strain between the substituents on the 1 and 3 carbon, respectively. Okay, so that's where that name comes from. Okay, it's diaxial because it's 2 axial groups that are kind of, parallel or overlapping each other. Okay, if you're having trouble seeing it, drawing a Newman projection might show it a little bit better. So you can see that here in the, if you want to see how this diaxial strain comes about, you can kind of see this gauche interaction kind of bringing it about. Okay, whereas in the case of an equatorial group, you can see that it's more of an anti-interaction, okay, which is much more stable. And of course, the larger the group, the bulkier the group, the more that overlap is going to destabilize your system. Okay, so you can see here as we get larger and larger groups, like chlorine is probably larger than it's a pretty large atom, but you can see that as we start getting to really bulky groups like this tert-butyl group, which is much much bigger than just a single atom, right? You can see how there's a huge favoring for the equatorial positioning of that tert-butyl group. Okay, now how do we represent these cyclohexane groups rather quickly and easily in our sort of geometric drawing of our cyclohexane as a hexagon, right? You want to use your dashes and your dash and solid wedges to show you where those groups are located, respective of the cyclohexane. All right. So if you're looking down on this cyclohexane, and this chlorine is pointing towards you, okay, that basically means that chlorine is pointing upwards here. So again, it's, if you're looking at your molecule like this, that's the equivalent of seeing of placing your eye over here and looking down on this molecule. So that's why this chlorine that's pointing towards you is shown with a solid wedge. Likewise, this methyl group that's pointing away from you is shown with a dashed wedge. Now, keep in mind that you can still do a ring flip, and they'll go from having these groups being axial to being equatorial. Notice that this still holds true. So you're still looking down on this. Okay, so your eye is over here. Notice that this chlorine is still pointing towards you as opposed to the hydrogen that's pointing away from you. Likewise, this methyl group is still pointing away from you, okay, as opposed to this hydrogen that's pointing towards you. Okay, and that's why we use a dashed wedge for the methyl group, because it's pointing away from you, and a solid wedge for that chlorine that's pointing towards you. Okay, so it doesn't matter which way you draw your chair conformation, and whether you start off with your chlorine as axial or equatorial, you're still going to wind up with that same sort of dynamic between your chlorine and your methyl group. Okay? So the key thing to remembering this, if you want to see this relationship, is to try and alternate your carbons as being up or down. Okay, so here we've drawn this carbon with the chlorine as pointing upwards, right? Which means this carbon with the methyl group is pointing downwards. So if this is up, that chlorine is axial. If this is down, this methyl group is also axial. But if we treat it the other way, if this was a down carbon, down up, that chlorine is equatorial. up, down, this methyl group is also equatorial. Okay, so it sometimes helps to label your carbons as being up or down, and just alternating. Okay, and that will tell you. So this is, if this is an up carbon, up up tells you that this is axial. Okay, if this is down up, or sorry, down down, because it's pointing away from you, so down down is also axial. Okay, that's how we'd figured this out. Okay, now let's look at an example where we have two options for how we want to draw our molecule, and they're not equivalent. Okay, so for example, here, if we have an ethyl group that's pointing towards us and a methyl group that's pointing away from us, and there are two carbons away from each other. So now you've got to think about, again, what's their relationship to each other. So let's say we wanted to start off by drawing this ethyl group as pointing upwards or in its axial position. We could say, we want this ethyl group that's pointing towards us and therefore that's pointing upwards. If we have this carbon as an up carbon, okay, this is up up, so that's going to be axial. That's down and that's up. This is up down, right? This methyl group's pointing away from us, so it's pointing downwards, right? So if this is up up, that's axial. This is up down, which is equatorial. And we can see that here. This methyl group is equatorial and this one's axial. Now, when you do a ring flip, of course, this is going to be, down up. This axial ethyl group will become equatorial, as we can see here, and this equatorial methyl group will become axial. Right? All a ring flip does is it just flips things from being axial to equatorial and vice versa. Okay, so are these two molecules going to be, these two conformations, they're the same molecule but different conformations, which of these conformations is going to be more stable? Okay, in the previous example, if I go back, it was kind of a moot point, right? You could kind of say, oh, this one over here is going to be more stable because both of my bulky groups are equatorial. So what about this one? Which of these two is going to be more stable? Well, one of them has to be axial and one of them has to be equatorial. But remember, we want the bulkier group to be equatorial, right? That's the one that's going to cause the most diaxial strain if it were axial. So it makes more sense to have our ethyl group, which is larger than our methyl group, have that be equatorial and therefore keep it out of the way. Okay, so it turns out that this molecule on the right is more stable than this molecule on the left. So we actually see much more, of our molecule on the right than we do of the molecule on the left. Okay. Likewise, you could do something similar here, and you'd probably notice the same thing. We've got this bulky chlorine group, kind of where this methyl group is. Now the thing is that chlorine more or less bulky than the ethyl group, right? You want the bulkier of these two groups to be axial. To be equatorial, so it's out of the way, right? If it's axial, you're going to have that diaxial strain. So if you're having trouble seeing that, if we go back, you can see that a chlorine has about 2 kilojoule interaction with its 1,3 diaxial strain, and ethyl group has about an 8 kilojoule interaction. So this is probably bulkier than the chlorine. So in other words, you would see a similar effect. You'd want this ethyl group to also be equatorial. Okay, so the more stable molecule you'd see here would look like this with a chlorine instead of that methyl group. Okay, when you have two substituents on your ring and you want to describe their location relative to each other, their positioning relative to each other, we can use the prefix cis or trans to describe that, positioning. All right. The word cis means same, like the same side. Trans means opposites. Okay, so the cis isomer has both of these methyl groups on the same side of the ring. the trans isomer has them on opposite sides of the ring. Okay, so everyone see the difference there? You've got, if you imagine that this ring is kind of creating a border here going this way, okay, our methyl groups are both on the same side here, and that's where that cis designation comes in. Here they're on opposite sides, that's where that trans designation goes in. Okay. Now you can only use cis and trans when you have two substituents that are the same type of substituent here. So in this case we could use this because they're two methyl groups, right? If you have different groups, if you had different groups here, you could use the hydrogens to help you decide cis and trans as well. If you had 4 different groups here coming off these 2 carbons, there is a different designation called E and Z notation. We'll get into that in a later chapter. Okay, we won't use that here. I think we'll talk about that a little bit more when we get to the chapter on alkenes. But just understand that there is a system to help you describe things that way as well. Okay. So so when it comes to the relationship between these 2 isomers, by the way, these are not constitutional isomers, right? There's no way to ring flip a cis isomer into a trans isomer. You have to connect these things differently, okay? But we can't call them constitutional isomers because they are still connected to the 1 and 2 carbons respectively. Okay, so what's different is how these are located in space. Okay, this is a spatial relationship. And so this is, we call these stereoisomers. Okay, we'll talk about stereoisomerism in the next chapter, and you'll see that, you'll understand a little bit more about this. We'll also talk a little bit about enantiomers. I used that word earlier in this chapter. You'll understand more about what that means in the next chapter. Okay. With ring compounds, you can sometimes have multiple rings fused together. We've already talked about bicycloalkanes. There are other compounds that involve multiple fused rings, not just 2. Okay, so we call these, in general, the overall term for all of this is what we call polycyclic systems that have more than 1 ring. Okay. Here's an example of a polycyclic system with more than 2 rings. So if you look at diamond, it's basically a huge network of rings of carbon atoms connected together. Graphite might be another example of that too. Okay, so so something to keep in mind. You can see this even in this example of these steroids. So in steroid molecules, which are a type of lipid, right, you have this fused ring system. And all steroids have this. They have 3 6-membered rings and 1 5-membered ring, always fused in this pattern. Okay, what's attached to those rings, or what functional groups you have, that changes the different kinds of steroids. But that fused ring system is always the same. That template's always there. Okay, that's it for this chapter. So basically, so that completes chapter 4. We can go through some practice problems here, and of course, I recommend doing the textbook problems. So since this is the 4th chapter that we've completed, we won't have a chapter quiz for this chapter. We will have an exam instead on chapters 1 through 4. Okay, now to help you get ready there is a practice quiz on this chapter on Blackboard in the content area with answers at the end of it. So just like your other quizzes, I recommend using that to prepare for your exam. Go through those quizzes, including the practice quiz for this chapter, and see what you got wrong and use it to help direct your studying when it comes to this exam. Okay? All right. So in the meantime, though, let's go through the additional practice problems. So I will just skim through those and I'll put up the answers so you can check your work. Okay, so here we have a molecule and you want to name it. Here we have a name for a molecule, you want to draw it out. Okay, so with this first one, of course, identify that longest carbon chain, then identify your substituents, and then number your parent chain, and you know, add those locants to those substituents as you're writing it out. With this one, maybe start off with that root word nane and draw that out, and then draw the substituents using those locants to see where they branch off. Okay. So here are the answers to those two questions, right? So here it looks like they used one methyl ethyl to describe this. So first of all, I guess we should probably look for that longest carbon chain. You might be tempted to say, oh, I've got, starting from here, it's 1, 2, 3, 4, 5, 6, 7. But you realize if you start from either here or here, that gives you more carbons. 1, 2, 3, 4, 5, 6, 7, 8 carbons. So that's your parent chain. Now, you've got an isopropyl group here when you do that. So it looks like here they've used the name methyl ethyl as opposed to isopropyl. So you can see how that changes the alphabetical order depending on which name you use. So if you use isopropyl, you would put that after E but before M for methyl. If you have methyl ethyl, 1-methyl ethyl, that comes after methyl. Okay? All right. With this one, we draw a 9-carbon chain, and then you just draw your substituents off of it. So we've got four bromines, right? It's tetrabromo. And looking at this, you can see where they're all located on the numbers 1, 2, 6, and 7 carbons. So 1, 2, 6, and 7. And then we have 1,2-dichloroethyl. So you have an ethyl substituent, and there's a chlorine on that first carbon and a chlorine on that second carbon of that ethyl group. Okay, have a look at these two molecules and see if you can determine the relationship between them. Okay, are they isomers? Are they identical? Are they completely unrelated? You could try using a model to help play around with this, but I'd recommend at least trying to name these two molecules. That's kind of a surefire way to figure out this answer. So hopefully, as you name them, you realize that they are both named 2,5-dimethylheptane, which tells you that they are identical molecules. They have to be identical if they have identical names. Okay, this is a general question. We kind of talked about this earlier in the chapter with using heat of combustion to see relative stability of hydrocarbons. This comes down to hydrocarbons having, a more stable hydrocarbon has a lower potential energy. So since it's at a lower starting point, it gives off less heat when you burn it. Okay, so essentially the higher your heat of combustion, the less stable your hydrocarbon, and vice versa. Okay, here's a Newman projection for a molecule. Go ahead and draw its structure, and then try drawing, its highest energy conformation. Okay, so keep in mind that this point over here is a carbon, and the circle behind it is another carbon. Okay, so you're looking down that carbon-carbon bond. So think about what's attached to those carbons. Okay, so if it helps when you're drawing this, it might help to start off with that carbon, with a line representing that carbon-carbon bond, and then ask yourself what's attached to each of those carbons. So if I imagine that this front carbon is this carbon on the left, if I'm drawing this normally, it looks like I've got a methyl group sticking off of that, okay, and that's pointing to my left, okay, so that's pointing downwards and away, okay, and then this carbon and this carbon, which is, that's kind of wedged away there, sorry, this is kind of a messy drawing, these two carbons are connected to each other by this sort of 3-carbon bridge. Okay, so this is going to be a very messy drawing, so I'm going to probably want to redraw this so that this bond is pointing elsewhere. Okay, on this back carbon, it looks like I have a ethyl group pointing downwards, right? I have a hydrogen, which I'm not going to show, and I'm going to have an ethyl group pointing to my left, upwards and to my left, so kind of, like that. Okay, so if I were to redraw this, okay, I could draw, maybe it might be easier to start off with this pentagon. Okay, so start off with this group, okay, and that's this carbon here, And I know I have one carbon sticking off of it, another carbon sticking out there. Okay, so this bond here is this bond over here, and this carbon that's pointing away from me is this methyl group I've drawn here. And of course here I've got the other two ethyl groups. Okay, so not showing any stereochemistry. This is kind of what this looks like basically. Okay. Of course, if you want to draw it in higher or lower energy conformations, the highest energy conformation will have both of these ethyl groups overlapping with this bulky cyclopentyl group. Okay, the way this is drawn right now is probably the lowest energy conformation because it has these like kind of far away from each other. But yeah, if you drew those two, those two ethyl groups staggered, or sorry, eclipsed by this cyclopentyl group, then that would be a higher energy conformation. Okay, so yeah, so there's your answer. So there's your lowest energy conformation as it was drawn. That's what it looks like as the highest energy conformation. Okay, so go ahead and draw the high. So ask yourself, how would you want to draw this as with a higher energy, lower conformation, the highest in energy, lowest conformation. Keep in mind the bulkiest group here we have is this tert-butyl group. So essentially the highest energy conformation would probably have that axial, and the lowest energy conformation would probably have that equatorial. Okay, so you probably want to think about how would I draw this so that it's axial or equatorial. Okay, so if I want this to be axial, now notice that this is pointing towards me. So imagine that's an up group. I would want this carbon to be an up carbon for this to be axial. Okay, so if I'm trying to draw that, and I want this group, this bulky group, to be axial, and it's pointing upwards towards me, I want this to be an up carbon. So this is a down carbon, this is up, this is down, this is up, and this is down. Okay, so if this is up, up, so that's axial, this group is down, up, so this is going to be equatorial. This is going to be up, up, this is also axial. Okay, this will be the highest energy conformation when I draw it out. And if I do a ring flip of it, that would be the lowest energy conformation. Okay? So when I'm drawing this out, so there's my chair. Okay? Let's say I have this this carbon is towards my right. So there's my tert-butyl group, and I want this axial. Okay, there's my tert-butyl group, and that's pretty unstable. So if I'm going clockwise around that, this is going to be my equatorial methyl group here. So 1, 2, 3, 4 carbon. 1, 2, 3, 4, 5 carbons in. So that's this one. We want this axial as well. That's an upward pointing carbon. So this one's also going to be pointing upwards. Oops. There we go. Okay, so that's our highest energy conformations. And of course, if we do a ring flip, okay, this is going to be equatorial. This, which is going to be axial, will be pointing upwards like that. And this one's going to be equatorial. It's kind of hard to see because it's going to be pointing away like that, but that's where it looks like equatorially. Okay, so a better diagram would look like that. But that's kind of essentially what we're trying to draw here. So again, notice here with this being, axial, this is the highest energy conformation. This group being equatorial is the lower energy conformation.